In this video, we're going to go through at least a couple of the examples in the course pack. Before we do that, though, I'd like to take a minute and just remind you of something. Once upon a time, we said if f of x was equal to e to the power of x, then we could describe the Taylor polynomial for this as t sub n of x is equal to e to the power of b, that's my f of b term, plus the first derivative of f, which is e to the x, evaluated at b, times x minus b, plus 1 over 2 factorial times the second derivative of f, which is e to the x, evaluated at b, times x minus b squared, plus, I think I'll do one more. As I said in a previous video, we don't usually do all this many terms when we're writing it out because you can see the pattern, or the hope is that you can see the pattern, and you don't need to see all of these terms written out like this, but it doesn't hurt. And of course, this can go on indefinitely, so I'll have for my last term 1 over n factorial e to the power of b, that's the nth derivative of e to the x, evaluated at b, times x minus b to the power of n. Now, if b is equal to 0, then we get t sub n of x is equal to e to the power of 0 plus e to the power of 0 times x minus 0 plus 1 over 2 factorial times e to the power of 0 times x minus 0 squared plus 1 over 3 factorial e to the power of 0 x minus 0 cubed, and so on, up to 1 over n factorial times e to the power of 0 times x minus 0 to the power of n. I can tidy this up even more by saying that's just 1 plus x plus, let's write it as x squared over 2 factorial plus x cubed over 3 factorial plus, and so on, up to x to the power of n over n factorial. And if I want to, I can choose to write x as x to the power of 1 over 1, or 1 factorial. And I can even write this term as x to the power of 0, because anything except 0 to the power of 0 is 1, over 0 factorial, which we've defined as being equal to 1. And then that lets me write this as a series, a summation, as I goes from 0 to n of x to the power of I over I factorial. Okay, so that's the Taylor polynomial for e to the x, the function e to the x based at b equals 0. Let's talk about the error. I'm going to write it as error, and then I'll also write it as f of x minus t sub n of x. We know that this has to be less than or equal to some value m, and we did this in a previous video as well, so I'm not going to go into the detail for it here, but it's e to the x, because on an interval, e to the x is the value, the maximum value that can take on is e to the x, over, that's my m, over n plus 1 factorial times x to the power of n plus 1. Now, before we proceed, I want to do some work over here off to the side. I want to take a look at this thing that looks like this, x to the power of n over n factorial. I want to take its limit, I haven't given myself a lot of space here, limit as n goes to infinity. And my claim is that this is always going to be equal to 0. Why is this relevant? Well, if you look here, I have n plus 1, x to the power of n plus 1 over n plus 1 factorial. So if I just added 1 to this n here and 1 to this n here, this piece right here would match, right? And so my claim is that if this thing, the limit of this thing is as n goes to infinity is always 0, then this is going to always be equal to 0 as well. So bear with me. I'm going to start by rewriting just this piece right here. The absolute value of x to the power of n over n factorial can be written as, well, the x to the power of n part can be written as x times x n times. And the n factorial part can be written as n times n minus 1 times n minus 2 all the way down to 1. And if I reorder this and rewrite it instead as x over 1 times another copy of x over 2, and then another copy of x over 3 times another copy of x over 4, and so on, all the way up to n. So I just reversed the factors in the denominator here, and I split this up into n different, or I'm in the process of splitting this up into n different fractions, all of which are going to be multiplied. Well, but I'm going to stop short of n. I'm only going to go up to some number less than m. I'm going to keep multiplying until I get to x over m. All right. Then I'm going to multiply this by the next factor, which is m plus 1, right? X over m plus 1. So far I have my first term, my first factor, my second factor. All I've done is rewritten x to the n as x times x times x times x n times, and n factorial is n times 1 less than n times 1 less than that and 1 less than that, all the way down to 1. Then down here, I've reordered the factors so they're starting at 1 and going up instead of starting at n and going down. But I'm still having just x times x times x in the numerator. But I stopped halfway or somewhere short of n terms. I stopped somewhere before I got to n terms. And what I'm going to do is just kind of split this into two separate lists of factors. So I have m x over m plus 2. And I'm going to keep going now until I get to x over n. And I'll put parentheses around that as well. This is kind of akin to saying 1 times 2 times 3 times 4 times all the way up to 10 times 11 times 12, for example, is the same as 1 times 2 times 3 times 4 times 5 times 6 times 7 times 11 times 12, right? I stopped somewhere short of the last number. Forgot to put parentheses around that. Right? I didn't get all the way up to 12. I stopped somewhere short of that, but then I just carried on. This product here is the same as this product here. In the same way, this second product here is the same as this product here. I just kind of split it up into two lists. The difference between these two examples is that here I know exactly where I stopped. I stopped at 4 and picked up again at 5. Here I don't know. Somewhere between 1 and n, I stopped, split my product into two different products, which when you multiply them together still gives you this, but I wrote it as two separate products and I stopped at m. Okay, now I'm going to put a stipulation on m. I'm going to make it so that m has to be bigger than 2 times x, or 2 times the absolute value of x. And if that's true, then at some point for some value of m, it's going to be true, something bigger than that. Each one of these is going to be less than or equal to 1/2. Here's kind of why that's the case. If m is bigger than 2x, then 1/2 m is bigger than x. Right? All I've done here is multiply both sides of this inequality by 1/2. Now if I change the direction we're going in here, and I write this as the absolute value of x is less than 1/2 m, then what I'm saying is that the thing you see in each numerator here, this absolute value of x, is less than or equal to half of m. And that means that this whole, not less than or equal to, sorry, just strictly less than. That means that this whole expression is less than x over 1 times x over 2 up to x over m times 1/2 times 1/2 up to n times a half, n times, well, n minus m times, right? We have, this is everything in this list. There's n things in this list. All of these and all of these together, there are n of them. If we take the first m of them, then what's left is n minus m terms, or factors rather. So there are n minus m copies of 1/2 here. So now we'll rewrite this as x over 1 times x over 2 times up to x over m times 1/2 to the power of n minus m, n minus m. So now we have this collection of factors here, and this collection of factors here. And the bigger n is, the closer this product, right? There's a half times a half times a half, this many times. If m and n are close together, then this is going to be, you know, if m and n have a difference of 3, then we're going to have an 1/8 here. If m and n have a difference of, I don't know, 5, then we'll have 1 over 32 here. But if n is a very large number, in fact, the larger it is, the farther away it is from m, the smaller this product, 1/2 to this power, the smaller this gets, to the extent that we can say that the limit as n goes to infinity of 1/2 to the power of n minus m, I'm having trouble writing my letters today, that limit is equal to 0. In other words, the bigger n gets here, the farther away it gets from m, this product approaches 0. The farther away we get from, these two numbers get from each other, the closer we get to 0. So the limit of this product is equal to 0. Well, this product right here, this piece of it, is just a part of this whole big product here. So what we're saying, essentially, is I'm gonna erase a little bit here and rewrite some stuff. What we're saying is that this big long product is equal to, let me back up even farther and say that the limit of this thing, which is what we're trying to determine here, right? The limit of this thing is equal to 0. The limit of this thing, the limit of this thing here is the limit of this product here. And so if I take the limit as n goes to infinity of x over 1 times x over 2 times x over m times 1/2 to the n minus m, and if the limit of this piece of it goes to 0, then the limit of the whole thing goes to 0. Remember from calculus, when did we do that? Calculus 1, I think. The limit of f of x times g, sorry, I started to write f again there. Limit of f of x times g of x as x approaches any number, actually, is equal to the limit as x approaches that number of f times the limit as x approaches that number of g. Now, we can't say this about derivatives. The derivative of f times g is not the derivative of f times the derivative of g. We have the product rule for that, but this is just limits. The limit of a product is the product of the two limits. And that's what we're using here. The limit of this big product here is the product of the limit of this thing, whatever it happens to be, times the limit of this thing. Well, the limit of this thing is 0. So I'm going to get the limit of this thing is 0 times anything else is going to be 0. So that proves that this limit up here is 0. Okay, now what I've just done here is demonstrated something called a lemma. I'm going to use this factoid, now that I've proved it, I'm going to use this fact in the rest of my demonstration down here. The idea of a lemma is something that you need, a fact that you need to use in a larger proof. This isn't really a proof down here. It's kind of a demonstration, an illustration. But oftentimes they're used inside a larger proof to kind of prove that something that you're going to claim in your larger proof is in fact true in and of itself. It's not so much that I'm interested in this fact in its own right. It's interesting, but it doesn't really help me except as a tool to make a demonstration of a larger point. So I'm going to take this lemma now, this fact that I have highlighted here, and I'm going to use it down here. If you notice, I've got, let's rewrite just this expression here. I have e to the x over n plus 1 factorial times x to the power of n plus 1. I could rewrite that as e to the power of x times x to the n plus 1 over n plus 1 factorial. And if it's true that the limit, not as x goes to, but as n goes to infinity, of x to the n over n factorial is equal to 0, then surely if I add one more, both there and here, right, n is just getting larger, or the thing in the position of n is getting larger. So as n goes to infinity, n plus 1 is also going to infinity. And as n goes to infinity, n plus 1 is going to infinity. I should put parentheses around that. So this is also true. And so now, if I look at this thing here, this is going to 0. And if this is going to 0, then the product is going to 0. Well, that was just another way to write this. And so what we're saying here is that the difference between the function and the Taylor polynomial for that function, for n terms, is 0. What does that mean? Well, it means that the Taylor polynomial is the function. So in this case, we have that the sum as I goes from 0 to infinity. Remember, that's a limit as sum goes from I to n, as n goes to infinity, of x to the power of n over n factorial is actually equal to e to the x. Not approximately, the Taylor polynomial, the sum of all terms, the Taylor series, in fact, the sum of all the terms as n goes to infinity is actually equal to e to the x. Kind of another way to say this is that the limit of the Taylor polynomial as n goes to infinity for the function f of x is equal to f of x. Now that's not true for every function f of x, but it is true for the function f of x equals e to the x. And it's true for several other interesting cases as well, which we'll talk about in just a minute. But the point here is that sometimes, under the right conditions, the Taylor polynomial, which is this thing right here, this is actually the Taylor series. We call it a series because it's a sum not just from 0 to n, but from 0 to infinity. This series, this Taylor series, is equal to the function it approximates, exactly equal to the function that it approximates. All right, so we've just shown that e to the x can be written as its Taylor series. There are a couple of others that are particularly interesting, and I'm going to go ahead and demonstrate one of them, not quite to the same extreme that I've just done with e to the x, but just as a matter of interest. Let's take a look at the Taylor polynomial for the cosine. The cosine of x can be approximated by the Taylor polynomial, and actually I want to go with the second Taylor polynomial here for reasons which will become obvious in a moment. 1 minus x squared over 2. And the reason I'm pointing this out is because we did this in section 2. Section 2 is where we learned about quadratic approximation. So the closest we could get in that section was an x squared kind of thing. Well, it turns out the next term here is going to be plus x to the 4th over 24. And I can rewrite that. That is now the third Taylor approximation, Taylor polynomial. So I'll change that to a 3. I could write this as x squared over 2 factorial and x to the 4th over 4 factorial. And in fact, I could write this as x to the 0 over 0 factorial. And so you can see here, the pattern is that we're only dealing with even exponents, right? 2, 4, and in fact 0 is also an even number because it's divisible by 2. It's not an odd number because it's not divisible by 1 more than 2. That's another class. So these are all even exponents and even factorial values, right? 0 factorial, 2 factorial, those are all even numbers. If I added another term, it would be minus x to the 8th over 8 factorial, and so on. One way to write this would be as the sum of x to the power of I. What's changing here is, first of all, the exponent, and then also the denominator. All right, so let me rewrite that a little bit. X to the power of I over I factorial. The problem is we have alternating signs as well. This term is positive, and then negative, and then positive, and then negative. So I need to find a way. Let me get my indices down here. I goes from 0 to, we're going to go ahead and say n, and that makes this the nth Taylor polynomial. But we need to figure out how to make the signs alternate. You know, right now this looks like x to the 0 over 0 factorial plus x to the 1 over 1 factorial plus x to the 2 over 2 factorial. First of all, there are two problems here. One is that all of the terms are positive, and in the actual Taylor polynomial, they are not. The other problem is that this term should not be here. So there are actually a couple of things that I need to do to change this. Notice that my I here is adding 1 each time I add a new term, when in fact I need to add 2. So if what I'm doing is producing a denominator that's an even number, then I need to make it an even number. The number 2i will always be an even number. So now when I plug in I equals 0, I get 0 factorial. When I plug in I equals 1, I get 1 times 2, 2 factorial. And then 4, and then, oh, I see I missed one up here. This should be minus x to the 6th over 6 factorial, and then plus x to the 8th over 8 factorial, and so on. Except that the terms are not just plus each time. It's plus and then minus and then plus and then minus and then plus, right? So there are two things we're doing here. One is to make sure that our denominators, and actually also our exponents here, are always going to be even numbers. So let's make that a 2i as well. And then the other thing is to make sure that each term has a different sign. Well, recall that the number -1, let's make it to the power of k for now. When k is 0, anything to the 0 power is 1, so that's going to be +1. When k is 1, I'm going to get -1. When k is 2, I get k squared. Oops, I get -1 squared, which is 1. When k is 3, I get -1. When k is 4, I get positive, and so on. So I can write for each value of I, I'm using k here, but I'm going to use I over here. If I put a -1 to the power of I in front of that, then when I is 0, I'm going to get to the 0 power, which is positive. Then I'm going to get to the 1 power, -1 to the 1 power is negative. To the 2 power will be positive, and then negative. So every time I add 1 to I, the sign changes. But every time I add 1 to I here, I'm actually adding 2 because I'm doubling I. I hope that makes sense. It's a little bit nuanced, but I hope that's going to make sense for you. Let's try this now. This didn't quite work, but let's try our newly built series and see if it works. I get -1 to the power of 0 times x to the 2 times 0 over 0 factorial. That's my first term. And that's going to be equal to 1 times x to the 0 over 0 factorial, which is 1. All right, now I'm going to do the next term. Remember that when you're doing a series, when you're doing summation like this, you're adding a term. You're adding each term on to the one before. So I'm going to use pluses here for now. But then I'm going to have for my next term negative 1 to the power of 1 times x to the power of 2 times 1 over 2 times 1 factorial. That's going to be equal to, and now erase this plus, because negative 1 to the power of 1 is negative 1, so it's going to be minus x squared over 2 times 1 is 2, so I get 2 factorial. Let's test at least one more here. My next term is going to be negative 1 to the power of 2 times x to the power of 2 times 2 over 2 times 2 factorial. What's changing here is the 0 here, here, and here, the 1 here, here, and here, the 2 here, here, and here. That's what's going from 0 to 1 to 2 and eventually all the way up to n. That's the thing that's changing, right? And that's because there's an I here, here, and here. So what do I get for my next term? Well, negative 1 to the power of 1. Negative 1 to the power of 2 is positive 1, so I'm going to get a plus x to the 4th over 2 times 2 is 4, so I get 4 factorial. And this does in fact match the first 3 terms I told you about up here. So what I have here now is this Taylor series for the cosine of x. So I'd be inclined to include something like this. The cosine of x is equal to, and I haven't shown that, I haven't proven this equality in this case, but I showed you how an equality might be proved on the previous screen with a different function. It turns out that cosine of x is another one that is equal to its Taylor series. And so the Taylor series converges to cosine of x. And there are a couple of others that I'll talk about here in just a minute, but the point I want to make here, the reason I did this exercise, the reason I did this work and this work down here was to show you how to build these, because sometimes you're going to be asked to build the guts of this series. There is an entire course that some of you at some point may take, if you're more of a pure math person. You may end up taking a course called number theory. And number theory is the study of integers and their behavior. And one of the things that comes up in number theory quite a bit is the behavior of odd and even integers. And so this is the kind of thing, this work with odd and even numbers and recognizing that 2i is always going to be an even number. That's the kind of thing that would come up in a course on in number theory, but not necessarily in a 1-credit course that's supposed to be part of a larger calculus class. So it's an interesting observation to make. It's a very handy observation to have in your back pocket. And I'm going to do another one now. I'm going to address the sine of x and show you the difference. And with the cosine of x, our powers and our denominators, our factorials, were all even, but with the sine of x, they're all odd. So I'm going to show you how to deal with that situation. Okay, on the previous screen, I showed you that 2i will always be an even number for I some integer. That's set notation. This just means that there's something in, an element of, a member of the set of things called integers. This I is in that set, so it's a member of that set. And what we're saying here is that 2 times any integer I, because I is an integer, this is 2 times any integer I. So no matter what the integer is, even if the integer itself is an odd number, when you double it, you're going to get an even number, right? So when I want to guarantee that I have an even number, I'm going to say 2i. For some integer I, for some I in the set of integers, 2i is an even number. And if you think about the even numbers, you get things like 2, 4, 6, 8. And what's missing is the numbers in between, 3, 5, 7, and so on, right? What's different about these numbers down here from these numbers up here is that each one of these is one more, or one less, you could argue, from one of the even numbers. So if 2i is always even for I in the integers, then how do you write an odd number? Well, it's pretty much just what I said. You say that for each integer I, double it and then add 1, and you'll end up with, the result of this will always be an odd number. For the sake of transparency and completeness, it's not uncommon to see 2i minus 1. Where you see that will depend on exactly what context you're working in, which textbook you're using, who your instructor is, and all manner of other things. Both of these are true. If I is an integer, 2i is an even integer, and then either 2i plus 1 or 2i minus 1 is an odd integer. Okay, so knowing that, and knowing that the cosine of x is equal to this Taylor series, I going from 1 to infinity of negative 1 to the power of I times x to the power of 2i over 2i factorial. Then it turns out that the sine of x is equal to the series I equals 0 to infinity of negative 1. I'm going to leave the power for a moment. X to the power of, I'll leave that power as well, and I'll leave this, right? All I need to do here is make this even power and this even denominator factorial, make them odd. So I'm just going to say 2i plus 1 and 2i plus 1. And then it turns out that these alternate as well, so I can make this exponent on negative 1 just I. Each term, each individual term changes sign. When this is 0, I want this to be the coefficient to be 1. When it's 1, the second term, I want this to be negative 1. And then I want them to alternate. But I don't want x to the 1, x to the 2, x to the 3, x to the 4. I only want x to the 1, x to the 3, x to the 5 over 1 factorial, 3 factorial, 5 factorial, and so on. So these two results are very interesting, handy, like the e to the x result. They are equal to their Taylor series. The Taylor series is more than just an approximation. It is another way to write exactly the function you were approximating. We also have, from a previous screen, e to the x is equal to its series. When I get farther down onto the screen, it's harder to control my pen and how it works. So I get x to the I over I factorial. So here's a third nifty result. So hang on to those. Those are very useful, like little nuggets of information you can pull out and look at every once in a while, and they may come in handy. Depends on what sort of field or what industry you're going into, but they're very, very nifty little things to have. If you take a note card with you everywhere that's got formulas on it, those would be really nice things to add to your note card. There's one more we need to talk about, and that is this one. 1 over 1 minus x is equal to its Taylor series, I equals 1 to infinity, just x to the I. Now, we have to be careful with this one, because let me show you by going back over one of the other ones. The terms here look like this. X to the 1 over 1 factorial plus x to the 2 over 2 factorial plus x to the 3 over 3 factorial plus, and so on, right? And we're going to do this, theoretically, an infinite number of times. We're going to have an infinite number of terms here. I is changing as one integer to the next, right? I is changing from 0 to 1. I forgot the 0 term here, actually. This should include plus x to the 0, which is 1, over 0 factorial, which is 1. So this would be 1 plus x plus 1/2 x squared plus 1/6 x cubed, and so on. With this one, though, the bigger I gets, right, we're getting bigger and bigger and bigger values of I here. Notice that as x gets bigger and as I gets bigger, both of these things get bigger. Remember, e to the x looks something like this, right? With this one, though, we're dealing with a fraction here. So if I keep adding x to the 1, x to the 2, x to the 3, x to the 4, this is going to keep getting bigger. But 1 over x to the 1, 1 over x to the, if there's a 1 here, well, first of all, there can't be a 1 here because then I'd be dividing by 0. But if there was a 2 here, and then a 3, and then a 4, and then a 5, right? The x, as x gets bigger, and as I get bigger, these things don't match, right? So this is true, but it's only true for values of x for which this thing keeps getting smaller. And again, I'll remind you very quickly what the graph of this thing looks like. 1 over x looks like this. 1 over negative x looks something like this. And that would be, see, my white graph here is 1 over x. My yellow graph is 1 over negative x. And now I'm going to graph, let's see, I'll do it in, I don't know, I think I'll do it in green. 1 over negative x minus 1. And I'm doing it that way because a negative times a negative is a positive. I've got a positive 1 here, but I've got a negative x, right? So what I want is a graph that looks like my yellow x, my yellow graph, but shifted to the right 1 unit. So that's going to go here. This graph looks something like this. Well, it turns out that because this is a fraction, for this equality to be true, I have to be between -1 and +1. So I'm really only allowed to work in this very small window. Oops, wrong pen, hang on. In this small window here, between -1 and 1, because between -1 and 1, except for 0, everything in here is a fraction. And fractions get smaller as x gets bigger. So for this equality, for this Taylor series, I have to say for x, values of x between -1 and 1, and not including 1 or -1, because at that point they're no longer fractions, right? You could argue, mathematically speaking, you could argue that 3/2 is a fraction. Yes, it's a fraction, but it's greater than 1. It's a fraction greater than 1. -3/2 is a fraction whose magnitude is greater than 1. So when I'm talking about fractions, I mean fractions that are less than 1. And those only occur between -1 and 1. So we're restricted to that collection of values for x. As it turns out, and this is an important point to make, that unless you have a restriction like this, it's true that this equality, this Taylor series here, is equal to the cosine for every value of x. Okay, so if I plug in the value of pi over 2 here, and I replace this x with pi over 2, and then I start adding up my i's, right, changing my i's and adding my terms, I'm going to get a true statement. Equally, if I replace x with 0, or 2 pi, or 3 pi over 5, or any other value of x, this equality is going to hold. The same is true for the sine and e to the x. It's not true for this one. It's only true for x values between -1 and 1, and not including -1 or 1. This interval is what we call the radius of convergence. So the radius of convergence for 1 over 1 minus x is 1, -1 to 1. So the radius of convergence is defined as the set of all x values for which the series converges. So let me just write that down. The radius of convergence is the set of all x values for which a series converges. It's the set of all x values. So in this example, the set of all x values for which this equality is true, for which this summation, this series, converges to the function, the set of all x values for which this series is equal to the original function, more than just an approximation, it's equal. The set of x values that makes that true are just the values between -1 and 1. That's what makes the radius of convergence -1 to 1, the interval between -1 and 1, and not including either of those endpoints. Okay, here's one more example. Find the Maclaurin series for the function f of x equals 2 over the quantity 3x minus 5. Well, the first thing to point out here is that the Maclaurin series is just a fancy name for a Taylor series that has a base of 0. Okay, so this is just the Taylor series where b equals 0. We can start by finding the Taylor polynomial for the function where b equals 0. The Taylor polynomial is going to be, well, let's see, f evaluated at b plus f prime evaluated at b times x minus b to the power of 1 plus f double prime evaluated at b times x minus b to the power of 2, and so on, up to the nth derivative of f at b times x minus b to the power of n. And we know f of x, it's 2 over 3x minus 5. I think because we're going to need to differentiate, right? I can tell you we're going to need to differentiate here. So let's rewrite f of x as 2 times 3x minus 5 to the power of 1, or -1 rather. And that gives us f prime of x is equal to 2 times -1 times 3x minus 5, wrong pen, 3x minus 5 to the power of -2 times the derivative of the inside function, chain rule. So that's -6 times 3x minus 5 to the power of -2. And f double prime will be -6 times 2, which is -12, times 3x minus 5 to the power of -3, that should be a negative, times 3, which gives me -36 times 3x minus 5 to the power of -3. The problem is I'm not just trying to figure out what these individual terms are this time. I'm trying to figure out how to write the nth term, because it's the nth term that gives me the pattern I need to be able to write the guts, if you will, of the series, right? I want to be able to write this thing as the series of something as I goes from 0 to infinity. And the something it's going to come from what this nth term looks like, right? There's a few adjustments we have to make, but if we know what this nth term looks like, then we can fill this in. In order to know what the nth term looks like, we need to know what the pattern is, right? And that's not obvious here. So let me erase this, and I'm going to redo my derivatives because I want to be able to see more than I've really got here. F of x is equal to 2 times 3x minus 5 to the power of -1. F prime of x is equal to, I'll write it as, let's see, I'll write it as -1 times 2 times 3x minus 5 to the power of -2 times 3. Now remember that 3 came from using the chain rule. I was taking the derivative of this product, or this thing here. It is a product, but the derivative of the first function is 0, so you don't have to worry about that. But when I take the derivative of this thing, this factor, I have to take the derivative of the inside function. So that's where the 3 came from. Let's do another one. I'm going to give myself a little bit more room here. The second derivative of this thing is going to be equal to, well, let's see, where did I get this -1 that I'm leading with in the previous one? That came from my exponent on the previous line. So let's do the same thing. My exponent on the previous line was -2, so I'll bring that down in front, -2 times, and then I'll have a 3x minus 5 to the -3, right? And then, let's see, where am I? So I've brought my exponent down in front, but then where did I get this 2? Well, this 2 came from basically having copied down the coefficient or the constant that was out in front here. The constant that's out in front this time, though, is negative 1 times 2. So times negative 1 times 2. And then part of the constant, although it's in a different place, part of the constant that I just need to copy down is this 3. So I'm going to have a times 3, which is part of copying down the constant that's in front of the thing you're differentiating, right? But then when I differentiate this thing, I'm going to have a times 3 from the chain rule. So I'm going to have times 3 again. All right, let's do at least one more. I keep moving a little farther to the left because I know it's going to take me more space each time. Once again, the leading number here, the negative 1 in this case and the negative 2 in this case, came from having brought down my exponent. So I'm going to do that again and bring down my negative 3. And then the next thing I wrote here was this 2, which was the constant in front. On this line here, I wrote down negative 1 times 2, which was the constant in front on the previous line. So for this derivative, I'm going to write down the constant that's up in front here, which is negative 2 times negative 1 times 2. And then I'll have my 3x minus 5. I'm taking the derivative, so I'm going to subtract 1 from the exponent. I didn't do it at the time, but part of my constant factor is this 3 times 3, so I'll write that as 3 squared. But then because I'm differentiating, I need to take the derivative of the inside function, so I'm going to have times 3 again. I would do one more, except that I think it may be enough to say that at least I think I can see the pattern now. So let's try to build the nth derivative of x based on what we know about the first, second, and third derivatives. The first and most obvious thing to me is that there's always a 3x minus 5 to some power. And that power, in this case it's minus 4, minus 3, minus 2, that power is numerically always one more than the number of derivative that we're on. Right, so here I'm taking the third derivative, and here I have a 4. Here I'm taking the second derivative, but in the exponent I have a 3. So if I'm on the nth derivative, then the numerical value of my exponent here is going to be n plus 1. But notice that each one of those was negative, right? It's numerically one more than the derivative, but at every single time it's negative. So I've got a negative n plus 1 for my derivative, for my exponent. Now something else that I can notice here is that this 3 is to the first power, and then to the second power, and then to the third power, and that power seems to match the number of derivative that I'm on. So it looks like I'm going to have a 3 to the power of n as a factor in my nth derivative. All right, so now it looks like I've got from this 3x minus 5 back, 3x minus 5 back towards the end of the thing. Let's see if we can work our way forward. What goes in front is, first of all, notice there's always a 2, and just a 2. It's not raised to any power, it's not, doesn't appear more than one time, just a 2. The other thing, though, is that there's always some other number. There's no other number here, but there's a negative 1 here, and then there's a negative 1 and a negative 2 in this one. In the next one, there's a negative 1, a negative 2, and a negative 3. The highest numerical value seems to match the derivative that I'm on. So if I'm the third derivative, the highest value here is 3, numerically. But they're all negative. So on one hand, it looks like I have 1 times 2 times 3, which is n factorial. But because they're all negative, there's no way to write that as negative n factorial. That doesn't make sense. So I'm going to change the way it's written here. I'm going to write this as negative 1 times 3 times negative 1 times 2 times negative 1 times 1. And then I'm going to rewrite the order that this is in. I have negative 1 times negative 1 times negative 1 times 3 times 2 times 1. And this piece certainly is n factorial. So I'll put my n factorial in there. And then this negative 1, let's see, there are three factors here, so there are three negatives, three negative ones. There are two factors that have negatives in them here, so there are two negatives. So it looks like the number of negative ones matches the number of the derivative that I'm on. So I'm going to have negative 1 to the power of n. Now, I want to tidy this up a little bit. I can write this nth derivative as, I think I'll go with 2 times 3 to the n times negative 1 to the n times n factorial times 3x minus 5 to the power of negative the quantity n plus 1. I could, arguably, also write this as 2 times negative 3 to the power of n times n factorial, etc. So now I have the derivatives that I need to start writing my Taylor polynomial. I want to make the observation, I'm actually writing a Maclaurin series here, and the Maclaurin series just means that this b here is 0. So not only am I going to have just x and x squared and x to the power of n, but when I evaluate my function, each derivative, it's going to be evaluated at 0. So for my first term here, I'm going to have the original function, f of x, evaluated for x equals 0. Well, if x is 0, this whole thing here is 0, and I get negative 5 to the power of negative 1, which is 1 over negative 5. So 2 over negative 5. 2 over negative 5. Okay, let's take a look at the next term. The next term starts with the first derivative evaluated at b. Well, I have my first derivative here now, and if I evaluate it at b, I get b equals 0. I get a 0 here, so negative 5 to the negative 2. Well, negative 5 squared is 25. I think I'll just write that as 5 times 5. Negative 5 times negative 5, but it's to the power of negative 2, which means it's 1 over negative 5 times negative 5. Okay, so evaluated at b, evaluated at 0, my first derivative, I get negative 5 times negative 5 under a 1. I have a negative 1 times 2 in front of that, and I have a times 3. So that's going to be, I think I'll write it as negative 1 times 2 times 3. And in fact, I think I'll write it in front. Negative 1 times 2 times 3. I think I'm also going to highlight this first term in one color and the second term in a different color so that when I look back at this, I'll be able to spot the pattern a little bit more easily. When I write once I've written my third term, I'll go back and highlight that in a different color as well. So let's write, are we done with the first term or with the second term? I have my f prime evaluated at b. That's negative 1 times 2 times 2, 1 over negative 5 squared times 3. That's all I have here. I don't have my x yet. X minus 0 is x. And let me go ahead and include that in my highlight. All right, so that's my second term. My third term, and I've just noticed that yet again, I have left out my 1 over 2 factorial. I'm actually really good at forgetting to include that. This is also going to affect my all of the subsequent terms, right? Each one of those is going to be 1 over, the first one will be, this one's 1 over 2 factorial, the next one will be 1 over 3 factorial. So the last one is 1 over n factorial. N factorial. And then that is added to, there we go, that's more accurate. So my next term then is going to be 1 over 2 factorial times the second derivative evaluated at b. I'll go back and then evaluate this at b equals 0 in just a minute, times x minus 0, or x squared. So I'll have an x squared at the end. So what goes in here is what I get when I evaluate this at 0. Well, this is going to be negative 5 to the power of negative 3, which is 1 over, and I think I'm going to start writing this as negative 5 to the power of, this could very easily be rewritten as negative 5 to the power of 2. 1 over negative 5 to the power of 2. Let's see, second derivative. So I'm on this line here. Then I have a 3 squared. Let's move this x squared over a little bit. So I have this thing here, and I have this 3 squared, and I need a 2 times negative 1 times negative 2. 2 times negative 1 times negative 2. All right, let's highlight that one. I think I'll use green. And I could do another one. I have a third derivative here. If I evaluate this, I get 1 over negative 5 to the power of 4. I get 3 cubed. But clearly, you can see that the work of this thing has already been done, right? I have what my nth derivative looks like. So I know what goes here. I know I have to preclude it with this 1 over n factorial, and I know it's going to have an x to the n at the end. So let's try writing that nth term. It's going to be 1 over n factorial. We know it's going to have an x to the n at the end. So what I've done so far is this 1 over n factorial and this x to the n. So now I have to figure out what the nth derivative of f at b is. Well, b is 0. So I'm just going to plug b in 0 in for x here. Well, everything else, the only thing that has any n's in it, sorry, the only thing that has any x's in it is this thing right here. So I'm going to get that negative 5 to the power of, and then I have all this coefficient stuff as well. Notice, first of all, well, let's just go ahead and write it as it is. Times 2 times negative 3 to the power of n times n factorial times 0 minus 5 to the power of negative n plus 1. So negative 5 to the power of n plus 1. Okay, so that's my nth term. And notice that in this case, at least, my n factorial and my 1 over n factorial cancel. Remember that n factorial, let's go with 1 over 4 factorial. Whatever that quantity is, it's equal, right? But even if you didn't believe that, I could show you that this is just 4 times 3 times 2 times 1, and this is just 4 times 3 times 2 times 1, and then the 4's cancel, and the 3's cancel, and the 2's cancel, and the 1's cancel, right? So this 4 factorial over 4 factorial, n factorial over n factorial, these cancel out. So now that I have that, I can tidy that up. This nth term, anyway, is 2 over negative 5 to the power of n plus 1 times 3, negative 3 to the power of n times x to the power of n. Well, everything's to the power of n except for this. So I can deal with that because I want to tidy this up as much as possible by pulling out one copy of that negative 5. I'm going to write that as 2 over 5. That negative in there, in front there, came from this actually being 2 over negative 5. And then what's left is negative 3 to the power of n times x to the power of n over negative 5 to the power of n. And that lets me write this as an entire, sort of a much simplified fraction. Also, negative divided by negative is a positive, so I get that. This is what my nth term looks like. Let's get a highlighter here. This is my nth term. Well, if that's my nth term, then I can use it to represent my first and my second and my third term as well. All I have to do is say, take negative 2/5 times 3x over 5, raise that to the ith power, and then add these all up. Now, when I is 0, I get stuff to the 0th power is 1. 1 times negative 2/5 is negative 2/5. When I is 1, I get negative 2/5 times 3/5 x. Let's see. When I is 1, I get 3 over 5. There's a negative times a negative is a positive. There's my 3 over 5 to the power of 1 times 2 over negative 5. There's 2 over negative 5. So I've accounted for this negative 1 and this negative 5 and this positive 3. I've accounted for this 2 and this negative 5, and then I just have x to the power of 1. When I is 2, first of all, notice that I have negative 2 times negative 1, which is equivalent to 2 times 1. And here I have over 2 times 1. So this factor here and these two factors here cancel each other out. I have a 2, which is 2 right here. I have an x squared and a 3 squared. So I have an x to the 2 and a 3 to the 2. And then I used one of these copies of negative 5 down here. I have 2 of them left. So I have negative 5 times negative 5, or positive 5 squared. Right? That 5 times 5 is, negative 5 times negative 5 is the same as 5 times 5 to the power of 2. So this all works out for I equals 0, 1, and 2. And so we have a pretty high level of confidence now going forward, saying that this is our Maclaurin series. The one other thing that I might do here is pull this constant out front. Not strictly speaking necessary, but it's kind of nice, because that doesn't change as I grows. So ultimately, I would say that this is my very nicest version of a Maclaurin series for the function f of x equals 2 over 3x minus 5. And I will say that I think that's a pretty good representation of the process that it's going to take to find these things. But there will also be times when you'll be asked to find the interval of convergence for a series. And so on the next slide, we're going to find the interval of convergence for the series that we've just found here. So if we want to find the interval of convergence for a series, and this is just the series we found on the previous screen, so it's the same problem that we were working on before, but instead of now finding the series, I want to find the interval of convergence for that series. Then one of the things we might want to consider doing is rewriting this as the sum that we know it to be. And that is, for I equals 0, we get 1. For I equals 1, we get 3x over 5. For I equals 2, we get 3x over 5 squared. And you can see now why it's nice to have written this as concisely as we did, because it's going to take a lot less energy and effort to write out each term. Let's add an nth term here. So we're going to add this all the way up to 3x over 5 to the power of n. Now, if I do a u substitution for 3x over 5, I get something that looks like this: negative 2/5 times 1 plus u squared plus up to u to the power of n. Again, simpler still. And so what we really have then is that this thing here is equal to negative 2/5 times the sum, as I goes from 0 to infinity, of u to the power of I. If we then take the limit of negative 2/5 times the sum from I goes from 0 to infinity of u to the I, then using the limit laws, we can pull that 2/5 out front. We have the limit as n goes to infinity. Oh, I see, I didn't include that down here. The limit as n goes to infinity of the sum, I going from 0 to infinity, of u to the I. Now, remember in a previous video, I think it was the one just before this one, where I showed you several series that converge to their functions. One of those was the series, the function 1 over 1 plus x. The series u to the k converges to that. So this is our u to the k, or u to the n power, except that we're using the index I here. So this is going to be equal to negative 2/5 times 1 over 1 minus u, because I have a u to the I here. This statement here, that this equals this, is now very useful. Except that, remember we said that for this to be true, u had to be, the absolute value of u had to be less than 1. Or another way to write this is that u had to be between negative 1 and 1. Well, u is 3x over 5. So let's back substitute. We get this statement. Multiplying both sides by 5 and dividing both sides by 3, I get negative 5/3 is less than x is less than 5/3. And that tells me that x, for this statement to be true, u must be less than 1, or the absolute value of u must be less than 1. And when you back substitute, you get that x must be between negative 5/3 and 5/3. So this interval of convergence is actually based on the interval of convergence of this series here. But the interval of convergence for the problem that we've just been working on is negative 5/3 to 5/3. We'll be talking more about intervals of convergence in the next video, but that should help you sort of see where they're coming from and get you ready for that conversation. So that's going to do it for this video, and with that, this section.